La verdad es que es un placer ver la sala así de llena y también con todas las personas que nos están siguiendo a través de Internet. Le voy a ceder la palabra muy brevemente al director del Centro Oceanográfico de Canarias para que nos ayude a impulsar este evento y después ya comenzaremos con las personas que tenemos aquí en la mesa inaugural. Gracias, Pedro. Pedro Vélez.
Buenos días. Muchísimas gracias a todos por acudir al Congreso de Vulcanología y aprovecho la ocasión también para dar la enhorabuena al equipo organizador y en particular obviamente a quien dirige toda esta acción de vulcanología submarina en Canarias en el marco del IEO, Eugenio Fraile, y esta fantástica iniciativa de poner todo el personal que tiene interés o trabaja de manera continua en vulcanología en Canarias. De modo que muchísimas gracias, espero que sea una jornada intensa y muy fructífera y para cualquier asunto que necesitéis estamos a vuestra disposición.
Muchas gracias, Pedro. Voy a hacer una breve introducción en inglés para todas las personas que nos están escuchando a través de Internet y bueno, las personas que están aquí también que no hablan español. So, good morning, everybody. I would like to warm welcome to all the participants in the third International Volcana Symposium, both attending in person and those who are joining online. It is a pleasure having you here in this event. Please note that this session will be conducted in Spanish, just 10 minutes in Spanish, so don't worry about that. And the rest of the presentation and discussion will follow in English. So we appreciate your understanding and we hope to find this symposium enrichment and instructive. Y ahora sí voy a dar paso a las personas que están en esta mesa. La verdad es que para mí es un placer contar con todos ustedes. En primer lugar tenemos a Néstor Padrón, que es el subdirector, lo está viendo ahí, nos sigue en videoconferencia, es el subdirector de Protección Civil y Emergencias del Gobierno de Canarias, quien ha dedicado su carrera al servicio público de la protección civil y a la gestión de emergencias en Canarias. Su amplia experiencia en emergencias está siendo clave para que Canarias se enfrente de la mejor manera a futuras emergencias. Gracias, Néstor, por acompañarnos y ahora te doy la palabra. También tenemos a Inés Galindo, que aparte de amiga y compañera, pues es una grandísima profesional. Ella es doctora en Ciencias Geológicas y es jefa de la unidad territorial del IPNA-CSIC en Canarias desde el año 2005. Eso no tenía que haberlo dicho. Y también fue la vicepresidenta de organización del Consejo Superior de Investigaciones Científicas. Inés ha sido una pieza central en la coordinación de emergencias volcánicas, liderando pues, todo lo acontecido en la erupción de La Palma, lo que la ha llevado a escalar en puestos de altísimo nivel en cuanto a gestión de la emergencia, siendo ahora la coordinadora nacional de emergencias del CSIC y también la presidenta del Comité de Asesoramiento de Emergencias. Gracias, Inés, por compartir este tiempo con nosotros. Y finalmente quiero presentarles también a una gran amiga y compañera que hemos llevado este simposio de la mano de hace ya 3 años, ¿verdad? Juntos, ella es Sharon Badhouse, es una formidable periodista y comunicadora científica, es fundadora y directora de GeoTenerife, que es una empresa pionera en la comunicación científica y en la formación de nuevas generaciones en tiempos de crisis. Por el otro lado, ha sido también fundamental para conectar las comunidades con la ciencia, especialmente durante los momentos críticos de la erupción de La Palma o del volcán Tahoe en 2021. Y ya les cedo las palabras de forma muy breve para que digan unas breves reflexiones o comentarios. Néstor, por favor.
Hola, muy buenos días. ¿Se me escucha bien?
Sí, perfectamente,
Néstor. Bueno, primero que nada quería pedir disculpas. Quería empezar mi intervención pidiendo disculpas porque tenía previsto estar presencialmente en el Symposium, pero bueno, un problemilla personal de última hora me ha impedido estar ahí, pero bueno, eso no implica que entre online y que de alguna manera, bueno, pues para mí sea un honor estar en representación de la Dirección General de Emergencias en este tercer Symposium organizado por el Instituto Español de Oceanografía en esas magníficas instalaciones que las conozco personalmente del Centro Oceanográfico de Canarias. Desde la Dirección General de Emergencias consideramos este evento de suma importancia por distintas razones. Indudablemente constituye un foro donde distintos expertos, destacados científicos nacionales e internacionales, bueno, se están congregando para compartir sus conocimientos y experiencias en vulcanología submarina y, bueno, en el caso que nos ocupa y nos preocupa a nosotros es la gestión de las emergencias volcánicas y, sin duda, su colaboración en el intercambio de ideas van a ser esenciales, ¿no?, para fortalecer nuestras capacidades de respuesta, especialmente ante este tipo de fenómenos naturales que tienen impactos significativos en nuestra sociedad y que no son probabilidades que puedan acontecer, son hechos reales, son situaciones que ya las hemos vivido en Canarias, en una sociedad moderna como la nuestra, una sociedad avanzada, donde ya contamos con distintos antecedentes. Y a mí profesional como personalmente me gustaría hacer alusión a un antecedente a la erupción submarina de la Restinga del 2011. Quizás porque fue la primera emergencia colectiva del siglo XXI en Canarias, en nuestro territorio, que nos recordó la importancia de fortalecer la protección civil a través de la evidencia científica. La necesidad de que los organismos científicos estuvieran junto a las autoridades en materia de protección civil a la hora de tomar decisiones, a la hora de asesorar sobre las distintas situaciones, y que nos recordó en aquel momento todo el asesoramiento científico, todo ese comité científico del plan de emergencias volcánico, bueno, pues una evidencia que parece que se había olvidado en aquel momento, ¿no? Y es que las Islas Canarias se habían formado por la acción de un vulcanismo prolongado en el tiempo, ¿no? Y eso se evidenció en aquel 2011, donde todos los que participamos en la emergencia aprendimos que la gestión de riesgo volcánico en Canarias debía ir acompañado de comisiones científicas asesoras, ¿no? Eso es muy importante y aún más si cabe en un medio donde la observación humana tenía mayores dificultades de análisis en su momento, como era el medio marino, ¿no? Tagoro nos brindó valiosas lecciones sobre la gestión de emergencias y sin duda favorecieron también una mejor gestión de la situación en el volcán Tajogaite en La Palma, ¿no?, en 2021. Y eso es algo significativo y que queríamos ponerlo de realce en esta presentación, porque este simposio, pues bueno, es una continuidad, ¿no?, en todo este proceso que estamos los últimos años avanzando en Canarias, en la gestión de emergencias volcánicas, una oportunidad única para aprender de los mejores en este campo y sobre todo para fortalecer nuestras propias prácticas, ¿no? No solo divulgativas, no solo educativas, sino también profesionales. Y es algo que agradecemos profundamente a todos los participantes, pero especialmente al Instituto Español de Oceanografía por continuar con este foro, evidentemente al Centro Superior de Investigaciones Científicas por mantener su apuesta efectiva, porque la ciencia esté junto a la gestión de las emergencias. Y bueno, quiero ir terminando esperando que este simposio pues sea una experiencia enriquecedora, ¿no?, para todos y que fomente, bueno, nuevas colaboraciones que beneficien no solo Canarias, sino a todas las regiones vulnerables en materia de actividad volcánica. Así que, sin más, muchísimas gracias y esperamos que sea un encuentro fructífero y lleno de descubrimientos, por supuesto.
Muchísimas gracias, Néstor, por tus palabras, la verdad que son realmente importantes. Solamente me gustaría recalcar que este Simposio Internacional VULCANA ha sido gestado desde el inicio siempre por dos organizaciones, que es el Instituto Español de Oceanografía y GeoTenerife, que está aquí la directora con nosotros. Por el resto, ahora le voy a dar la palabra también a Inés Galindo.
Bueno, buenos días a todos y a todas. A los que están aquí y a los que están online. Lo primero, quiero agradecer de verdad efusivamente a Eugenio, a Sharon y a Alba, que ha estado haciendo mucho trabajo ahí detrás, el haberme invitado a formar parte de esta mesa de inauguración. Cuando me invitaste pensé en todo el trabajo que estamos haciendo últimamente de emergencia y creo que es fundamental seguir trabajando en la volcanología, pero no solo superficial como normalmente se piensa, sino también la volcanología submarina. Néstor hablaba de la erupción del Taoro. Fue fundamental que estuviese el Instituto Español de Oceanografía allí, pudiendo hacer monitorización tanto de la parte abiótica como de la biótica, ¿no? Y yo creo que ha sido y sigue siendo un laboratorio natural fantástico. No hay que olvidar que las islas volcánicas son, el 90% de las islas está bajo el agua, ¿no? Entonces hay que dedicar recursos al estudio del volcanismo submarino y al estudio de la interfase entre lo superficial y lo submarino, que muchas veces queda ahí olvidado. El proyecto Vulcana en este sentido pues es fundamental, nos ha dado mucha información antes de las erupciones, durante y después. Es un sistema de monitorización de la evolución de los volcanes submarinos y bueno, yo quiero resaltar la parte de las emergencias por la parte que me toca, porque han estado ahí siempre, aparte, a ver, es un proyecto de investigación, pero cuando ha habido una emergencia han tenido la capacidad de movilizar sus barcos, de movilizar al personal, y eso la verdad es que es fundamental para poder dar un asesoramiento científico durante una emergencia que permita tomar decisiones a los gestores en base a la evidencia científica, ¿no? Entonces, no me quiero enrollar más porque se supone que tenemos que empezar la sesión a las 9:10, y así que nada, muchísimas gracias y espero que disfruten hoy del día y que aprendan mucho.
Muchas gracias, Inés. Y finalmente le voy a pasar la palabra a Sharon Bahaus.
Thank you, Eugenio. I'll be very brief because I'll be speaking quite a lot today. Ante nada, agradecer infinitamente a Eugenio, que ha desde un primer momento entendido y colaborado en una iniciativa que me parece increíble. El VulcanaSymposium desde un primer día ha sido gratis y abierto a todo público. Aquí estamos todos, puede venir cualquier persona, puede preguntar y puede participar. Y eso no es muy común en la comunidad científica. Y es una ventana increíble a lo mejor de la ciencia canaria internacionalmente. Tenemos delegates que se han apuntado de todo el mundo. Entonces, a todos los que están en la sala, que sepan que esto se está viendo en muchísimos países, luego se graba y se cuelga y tiene miles de views. ¿Por qué? Porque la ciencia de aquí es increíble. Y lo que es muy, muy apasionante este año es que se está agregando una sección sobre la dirección de emergencias. Y yo agradezco muchísimo que me hayan invitado a hablar sobre eso esta tarde, porque hay un elemento importantísimo aquí que en muchos territorios a veces se olvidan, y no es solo que trabajen en conjunto las autoridades y la comunidad científica, que es importantísima, desde luego, pero que se cuente también con las comunidades, con los impactos, sus experiencias y la forma de que ellos viven y forman resiliencia antes de estos eventos. Y de eso vamos a hablar, e invitamos a todos los que están también apuntados online que hagan sus preguntas, sus comentarios, que para eso está este foro tan increíble, que ya vamos por el tercer año, increíblemente, Eugenio, y te doy las gracias de corazón, because it's a fantastic initiative. So, without further ado, let's go.
Muchas gracias, Sharon. Y ya solamente para finalizar, me gustaría decirles a todos que para mí es un placer, bueno, agradecer primero a la organización, Juan Pablo, que te hemos dejado ahí solito, pero muchísimas gracias, Juan Pablo, Carmen, José Antonio, Bernardo, bueno, me voy a dejar a todos, Jesús, Eduard, Alba, por supuesto, ¿no? Y después también, pues, gracias, Pedro, porque también el apoyo de la dirección del centro es fundamental para que este proyecto salga adelante, así como la dirección a nivel nacional. Y, por supuesto, Inés Galindo, verdad, tus palabras la verdad es que me emocionan un montón, porque en época de crisis pues ahí se crean unos vínculos realmente especiales, ¿no? Y bueno, trabajar contigo es muy fácil, y además sobre todo en emergencia es muy fácil. Y Sharon, ¿qué voy a decir de ti? Pues que ha sido también realmente fácil trabajar contigo, y tenemos que poner, como muy bien acabas de decir, ese link, ¿no? No solamente la ciencia por un lado y la gestión de las emergencias por otro, sino todo de manera conjunta, y sobre todo tener muy en cuenta la visión y también lo que se traslada a la sociedad, que es realmente importante, porque si no la sociedad no sabe lo que estamos haciendo, pues siempre le crea duda de si se ha podido hacer mejor, peor, o qué es lo que está haciendo, ¿no? Entonces eso es fundamental, es algo que tenemos ahí que limar, duramente, y por eso tu visión es realmente importante. Yo no me quiero extender más, solamente quiero agradecerles nuevamente a todos el esfuerzo por venir, tanto presencial como de forma online, y bueno, que el proyecto Vulcana dure muchísimos años más, y ahora durante esta sesión vamos a dar una muestra muy modesta de lo que realmente hace Vulcana en el estudio multidisciplinar de los volcanes submarinos, ¿vale? Y bueno, y trasladarlo al resto del mundo. Nosotros, pues como Canarias y como España, pues tenemos un package, un presupuesto realmente limitado, pero con ese presupuesto limitado hacemos cosas realmente maravillosas, y eso es lo que queremos intentar transmitirle, nuestra modesta aportación a la ciencia y la vulcanología submarina. Muchas gracias y ya comenzamos.
Good morning. Okay. Well, welcome to the first session of the third International VulcanaSymposium, both to the present, those you are present here, and those who follow us by online. We are going to enjoy 4 talks during the morning before breakfast. Each talk will last around 20 minutes, and we will have after them some time for around 30 minutes for questions and comments. Well, let's start. I think Eugenio, my friend, will be the first speaker. You already know Eugenio Fraile from the Spanish Institute of Oceanography. He has been a close colleague of mine. We will be colleagues for many years. We work very closely in emergencies. He is a marine scientist based in Tenerife, and among his research lines, he leads the Volcano project that brings all together here today. The project is focused on the physical-chemical processes associated with submarine volcanoes and hydrothermal vents in the Canary Islands. His research has a strong component of scientific advisory, as we have talked previously, having led oceanographic studies conducted during several emergencies. Since 2014, he has served as an advisor to the National Cell for Risk and Threat Information and Analysis of the National Maritime Security Council of the Government of Spain on submarine volcanic risk, as well as on physical oceanography for the National Maritime Plan of the Ministry of Public Works. Additionally, he's also a member of the Canary Islands Volcanic Risk Plan, and recently he is working, as I said before, very closely with me as the National Coordinator for Marine Risk at CSIC. So, Eugenio, the floor is yours.
Thank you so much, Ines, for this presentation. Thank you, everybody, again, and I'm gonna, where is the, I'm sorry. Yeah, that happened with the first, I can see. I'm getting old, sorry.
I haven't said your presentation title. Eugenio is going to talk about the long-term oceanographic monitoring of the most recent eruptions in the Canary Islands. He's a great public speaker, so I know you are really going to enjoy.
Thank you so much. Well, let's see if I can start. So thank you so much, Ines, and thank you, everybody. As Ines said, I'm going to introduce a little bit the VULCANA project. And that VULCANA project is not a project just of one person, it's a project of a lot of persons that is involved in this macro project in order to study the physical, chemical, biological, and geological component of the submarine volcano and hydrothermal vents. So here you can see some of our colleagues. So the objective of VULCANA is to improve the scientific knowledge of the physical, chemical, biological, and geological processes associated with submarine volcano, but also with hydrothermal vents, and to be with application in the national and international context. And this is really important to do science, also to assess to the government for the future crisis. That this is one of the more important things. You cannot do assessment or advice without the science. In order to do that, because when you study the ocean, you have to do a fleet in order to go to the ocean and to take the samples. So the Spanish Institute of Oceanography has one of the more important oceanographic fleet of, well, actually the best oceanographic fleet. We've got several vessels, quite big, but also an ROV in order to reach that could reach the ocean to more than 2,000 meter depth. And actually, we are using also a submarine VULCANA that we've got here, the CEO of the submarine. So he's going to speak later about that. And also our ROV that can not only show us what is going on down the ocean, because as Ines said before, more than 90% of the submarine volcanoes in the Canary Islands are under the water. But if we cannot see, it seems like they are not exist, but they are, no? So they are there. So the ROV can show us the beauty of this submarine volcano and also allow us to research and monitor exactly in the places where they are emitting these anomalies. But also the fleet of the IEO have one of the biggest ships. Actually, it's the biggest one. Is Odon the one that is actually working, and so is in this month. So have been released. It's brand new, the ship, and it costs more than 85 million euros. And our monitoring is completely multidisciplinary from the point of view of the physical processes, chemical processes, biological processes, and also geological processes. So you can see here that in order to do that, you have to have a huge platform, multidisciplinary platform that is our vessel, in order to involve more than 20 persons at the same time and having all these measurements. But also we do some innovation, technology innovation that is really important in order to monitoring this event ad hoc. So we have developed with the help of some engineering that are also presented here for the ICSM. So several tools like our little minion that is called like that because it's yellow and it's quite small, but it's like a chamber that can contain hydrothermal vents in order to containing all the hydrothermal and to measuring with all different sensors. Also, we've got a different hydraulic shearing in order to obtain water samples. The first one was just able to take 1 liter, but this one is just, we are updated that, and we are able to obtain more than 6 liters at the same time. And finally, another instrument to obtain the vertical flux of the hydrothermal vents. As you can see, our monitoring is quite big around the Canary Islands. We were monitoring the Tagoro submarine volcano, of course, Henry Sea Mount, but also sea anomalies, La Palma, El Hierro, Volcán de Medio between Tenerife and Gran Canaria, and also Lanzarote. But there is a million of places that we're going to go. So the Canary Island base is more than 300 meter depth, and we have no problem at all in order to investigate all the points that are around the Canary Island. So you can see we've got in the last 13 years we were able to monitor or to conduct more than 39 oceanographic cruises, that this is a lot. If you just multiply every single cruise, it costs around 300,000 euros, between 300,000 and 600,000 euros. So if you multiply it for almost 40, it's going to be an amazing number. So this is just to let you know that the science in the sea costs a lot. So we are doing our best in order to get funding and to do it, but I need to thank also the Spanish Institute of Oceanography and our institution, the National Research Council, because they are supporting us. They believe us. They believe that this project was interesting for the society, and for this reason we've got this amount of money. Every single year, I have to say that we've got one of the biggest time series of monitoring a submarine volcano. Even in a pandemic year, in 2020, we could conduct one of these cruises. So with all this information, all this science, we were publishing some paper, manuscript, PhD, master thesis students, so you can see that this is some indicator, but also with the work that we were, the science that we were doing in the context of VULCANA project, we could advise in La Palma, and we've got also an honor, a medal honor for this advice that is also quite important. So just let's go to speak about the submarine volcanoes of El Hierro. As everybody knows, in July 2011, we have to go back in time for more than 13 years. So the island of El Hierro started moving a little bit, and feel more than 15,000 earthquake in these 3 months. And finally, the ocean crust broken at 1.8 kilometers south of La Restinga, that is a village that is here, starting the volcanic eruption. As you can see, it was a submarine volcano that was released a lot of heat, nutrient, ion, heavy metals, everything to the ocean, producing a huge perturbation in the whole water column. You can see this decoloration in the water column that was also following or monitoring via satellite. All this perturbation, this plume, this green plume, was a toxic plume with no oxygen at all and everything. And the perturbation was not only linked or close to the island of El Hierro, but also was moving with the circulation, with the dynamic of the ocean, with also interaction with some mesoscale activity and traveling hundreds of kilometers. So the perturbation was traveling also hundreds of kilometers. As you can see, the perturbation in the whole water column was dramatic. More than 90% of the flora and fauna was completely dead. Outside, you can see here, this is our little vessel. That is not little, it's 50 meters, so it's quite big. But all the perturbation, even the biggest one, couldn't resist and die in this situation. The geomorphology of Tagoro was completed defined in the last 6 months. In 6 months, a new building was built, more than 300 meters high, 1 kilometer of diameters, and more than 14 secondary craters. And the top of this volcano was only 88 meters, so just 88 meters more, and we've got another island of the Canary archipelago. And the more active crater is about 127 meter depth. So here you can see, and this is actually in the cards. So the submarine volcano produced like a natural laboratory in order to study how a marine ecosystem could resist or adapt to future climate change. As you may know, the 3 main stressors of climate change are the increase of temperature, the acidification of the ocean, and the desoxygenation of the ocean. So the increase of the temperature, the normal climate model predicted for the future, for the next 100 years, for the next century, the increase of the temperature is going to be in the ocean around 0.6 degrees. do you know how much temperature increase in the water column due to this eruption? You can see the face of our doctor here, no? It's like impression. So it's 18.8 degrees. So all the whole quarter was increasing for more than 80 degrees. But also the acidification, the climate model predict that for the next century, the reduction of the decreasing of the pH is going to be like 0.1, 0.3. And the emission of CO2 in the ocean by the volcano produce almost 3 points of pH. That is a lot. But not only this, the sulfur, the sulfur component that it was normally there's not a zero concentration. The concentration was around 100 micromolar. The CT was 470% more. The ion, the bioassimilable ion was 4 million times higher, and the PCO2 that in normal condition is 380 microatmosphere was more than 300,000 microatmospheres in the water column. And also the oxygenation, the future climate change say that for the next century it's going to be a reduction of 0.7 in the oxygen, and in the water column around El Hierro was more than 97%. So it was completely anoxic. So for this reason, the life couldn't be there, and they died. I'm going to be a little bit fast because I have no time at all. But I say that the nature is wise, because if there's some organisms that cannot live, there is another one that they can live. And this is the fact of this new Thiolaba veneris bacteria that have been found only for the first time worldwide just in Tagoro Submarine volcano, and it taking sulfur in order to obtain the energy. And well, here it is. This is a filamentic bacteria that are growing just in the Tagoro Submarine volcano. But there's not everything is bad. No? The submarine volcano during the first 6 months was emitting a lot of material, lava, heat, ion, everything to the ocean, no? Producing a really catastrophic condition. But after 6 months, the volcano became into an hydrothermal vent. So the anomalies were reducing quite a lot, and they were able to the life recolonize again. So it was a huge process of recolonization thanks to the temperature. Temperature was only 2 degrees. The nutrients were really, really high, more than 300 folds, and ion and everything. So everything that the life need to be concentrated and accumulated was taking place in this area. So right now we've got like an oasis of life. I always say that. So right now the submarine volcano Tagoro is a fantastic area here with a really big biodiversity and everything. Here, everything that I'm putting here is already published by our team. And actually, right now, the volcano is still active in the gasification phase. You can see here the evolution of the pH, for example. This is the pH in the 2014, 2015, 16, 17, 18, 21, and I put in the data for actually, but it's still active. You can see here, this is a transfer from here to here, so from the south to the north. So from the south to the north, there is nothing. We arrive to this box that is the center. Is here. You can see the big anomaly, so you can see all the time the same. No? So it's still present. We only are able to put a mooring inside the crater. This is the crater, and we put a mooring, we put it like that, and when we recover it, it's like this due to the huge amount of ion that is taking place. And you can see the anomaly that are still present in the area, no? 2.2 decrease, salinity decrease, decrease of pH of 1.2. And also another colleague that is doing the PhD with us, that doing also a huge research in the area, counting all the submarine vents there are more than 3,000 single vents in an area that more than 7,000 meters square that are producing a heat transfer to the ocean to do more than 2,000 megawatt. That is the equivalent of the 16% of the annual demand of the Canary Islands, just to put in order of magnitude. And now La Palma, so with all this knowledge, we were able to go to La Palma and to advise also to the government there. And our objectives were the same as El Hierro. We were there evaluating the process for more than 88 days with 3 different objectives: the characterization of the morphology of the seabed, the study of the physical-chemical property of the column water, and also to see the impact of the physical and chemical processes to the planktonic and bentonic species. So you can see the imagine, they were dramatic, and the population of La Palma was suffering a lot, but we were also suffering because the 28th of September, 10 days after the starting of the eruption, the lava flow reached the ocean. So as lover of the ocean, we were also we see that the perturbation were also arriving to the ocean. No? So here we can see in the first line, we were there monitoring 1 week before the lava reached the ocean. We were there just monitoring the ocean, and later when the lava arrived, we were able to measure again and to see the anomalies of the perturbation. We're working over there. We did also that Scott is gonna say later in the talk. We had the possibility to also do a specific research with the Pisces. Here you can see in the perturbation of all the material that were reaching the ocean. More than 53 hectares was the delta, the new delta in the super-area part, but also another 30 in the submarine ones. Here you can see the perturbation of the lava were reaching the ocean to more than 400 meter depths, and the distance from the coast, for the original coast, for more than 2.5 kilometers. And also here you can see our ROV working, and the huge pillow lava that Jose Antonio, another component of our team, is gonna tell us later in another talk. So we were able to obtain and to film for the first time all these construction, geological construction, and also to extract different rocks, sediment, hydroclasticity, everything from the surface to more than 4,000 meter depth. But also, you have to take into account that when you've got a lava delta with a temperature that more than 1,000 degrees, no, you cannot be approached with a vessel really close to it, but for security reason. But you need to measurements, so the only way to do it right now with the technology that we've got is to use a drone, and this drone could go really close to the lava delta and to take water sample for us, but also to put some sensor and to do it automatically for us. So it's no sense to risk or to put in risk the life of the person to go there, because we've got a special machine that can do it for us. And thanks to the collaboration also with the Geological Institute, we were able also to put the drones of this institution and to construct this, or to help to construct this kind of map that every day we're showing the different lava flows, and also help us with the observation of the lava flows and pillow lava down the ocean. Respecting to our physical monitoring, we were doing we were doing a specific observation here in the lava delta, and this is one of the manuscripts that ALBA have already published in 2014 that has that said that in several occasions, this is not the first time that the lava flows reach the ocean, and in other occasions, especially in Hawaii, have seen that when the lava flows came into the ocean, there's a huge perturbation, and this is an upwelling system. It's a physical process that bring water from the south for the deep layer to the ocean, and and produce a bloom, phytoplankton bloom. No, this is normal. But in this occasion in La Palma, we didn't see that. We saw that the physical process of the welling was producing, but the phytoplankton wasn't present. Actually, there was an abrupt chlorophyll decrease, so that more than 70%, and we think that this is due that the volcanism in Hawaii and Canary Islands are different, and here was a huge amount of ashes and hydroclastic that reduced the intensity of the light that can penetrate to the ocean. Here you can see here that the perturbation was not only in the surface but also in our ship, also dead fishes due to the ashes, and the submarine volcano El Hierro, that I'm not going to talk too much because Alba is going to do a specific talk about the submarine volcano of in Medio, that is between Tenerife and Gran Canaria. We can see that there is a fantastic volcano, and it's also, we've got some details that are active. And also the last one is that we were able to monitor if they want. Also. And Henry C. Mount, that is southeast of El Hierro. There is a submarine volcano, a mount that is more than 300 meter deep, and we did a collaboration together with the German people, and we discovered also that there was also several perturbations in some places of the volcano, so they've got also some hydrothermal activity. So I wanted to conclude my talk just with this to imagine. This is the lava, the new lava flow in 2021 in La Palma. You can see it's a black and white ecosystem, completely full of ashes and no life at all. But this is just 1 kilometer far away in the same delta, but for the other side, that is the delta of the eruption of 1929. You can see the huge biodiversity and productivity that are over there. So what I think that one imaging is better than 1,000 words, and with this imaging we wanted to transmit to the inhabitant of La Palma that just with a tiny time, the island of La Palma or the marine ecosystem of La Palma will be completely and fully recovered. So thank you so much for your time.
Thank you very much. Hi? ¿No? ¿No se oye? ¿Hola? ¿Ahora? ¿Hola? Ahora. Thank you very much for your presentation, Eugenio, and congratulations for the research you are doing and the new technologies that you have developed. Now we are supposed to have an online presentation. We hand over to Thibaut Barreyre. My French pronunciation is not good, but I would like to give him a warm welcome. But well, I'm presenting while they connect. Thibaut is going to explore how magmatic. Are you there?
Yeah, I'm here.
Hi,
can you guys hear me? Hello. Can you hear me well?
Yeah, I'm going to introduce you first. Okay.
Yeah.
Okay.
Sure.
Thank you. Well, he's going to explore how magmatic cycles modulate hydrothermal vent temperatures at the East Pacific rise, we change to another place. Thibaut has expertise in multidisciplinary research in the field of oceanography and marine geosciences. His research focuses on the interplay between subsurface flow and oceanic and crustal conditions that is fundamental for assessing energy budget, transport for deep sea relevant resources, and productivity of associated hydrothermal ecosystems. He approaches this topic through a mix of observational work, data analysis, and modeling, with the aim of integrating and reconciling complex flow observations into a coherent theoretical framework. Thank you, Thibaut, for sharing with us your research today.
Yeah, thank you. So let me just know if the sound is okay and the image is okay before I start.
Yeah, everything is right.
Okay.
Thank you.
And am I full screen for the slides?
Yes.
Yeah, okay. Awesome. Well, thank you very much for the invitation today. I'm actually very happy to be here, even though I'm online. Just a couple of words about me before I start to dive into the science. So at the moment, since less than a year now, I've joined CNRS back in France. Before I spent about 10 years ago.
Could you put the screen in full screen mode?
Sorry, what, full screen, there you go.
Let's see. No, we can
It's
see
good.
your slices, but...
Is it okay, Eugenio?
no, it's not. It's, we can see your slides. It's not in full screen.
Not full screen. Well, let me do entire screen. Sure.
If not, there's no
That
problem.
will be full screen now.
Let's try again. If not, you can do it like that.
Is it good?
It's loading.
Okay.
Oops.
Is it still loading on your hand?
Yeah, still loading.
Okay. No worries. That's
¿Tú tienes la presentación? Okay, now we got it. Oh, perfect. That's
oh, so it works.
it works right now.
Okay. Okay. Great. So I'll go ahead.
Yes.
Yeah. Okay. Perfect. Okay. Thank you. Well, I was saying thank you for having me today. I'm very happy to give this talk. I was saying that before joining CNRS back in France, I was 10 years abroad in Bergen, and that's actually where I somehow met and collaborate with Juan and Eugenio on a very cool project. And before that, I was in Woodsole, and some of the work I'm going to show you is part of my I would say like work and duty I have with the Woodsole Oceanographic Institution. So I'm going to talk about today magmatic system, but on the ridge, and I'm going to discuss how both the magma chamber and the magmatism of these volcanic ridges are linked to the fluid flow system, so the hydrothermal systems. And that's work I have with collaborators in US, but also in Europe. And that's a project funded by the National Science Foundation. And the image you see here is our submarine. So this one is not yellow, this one is Alvin. You can see like the white submarine here. And that's us at the Bio9 site. And that was last winter. And what you are seeing in the middle of the frame is a thermal temperature logger inside a black smoker. And we were recovering and redeploying sensors. And that's part of a project I'm going to discuss today. So we are about 2,500 meters at the seafloor here, depth. All right, so first of all, and the first talk from Eugenio was perfect to highlight the importance of studying hydrothermal systems, but also submarine volcanism, because of the energy and matter transfer you have from the deep earth to the overlying oceans. So the crust is actually a huge aquifer. 2 to 3% of the ocean volume is within the oceanic crust. It represents, those fluid transfer represent 25% of the total Earth heat loss. So its total is 43 terawatt. It's important vector of carbon transport, either CO2 or CH4, so important for climate, of course. It's associated with a lot of seismic and volcanic activity, as you could see and as you could experience yourself on the Canary Islands. It controls the hydration and the thermomechanical states of the oceanic crust. And obviously, it plays a very important role in the habitability and the limits of life, so what we call the deep biosphere. So there are many different fluid systems underwater. We have seen some images from the underwater volcanism. I'm going to mostly focus on what's happening on the ridge. So what you see here in the middle called hot vents and diffuse. And before doing that, I just want to make a quick stop and talk about one parameter that is very important for us. This one is called the permeability. The permeability, usually in K, is the parameter that controls the ability of the crust to allow a fluid to pass through it. So it's a very important parameter because it's linked to the temperature of the fluid, to the velocity of the fluid, and to the fluxes that are outputted by the systems. The problem with this parameter is that it's poorly constrained. We cannot have really like direct measurements. It's very hard to actually drill a zero crest earth. So, and there is a high variability due to both spatial and temporal scales. So that's kind of a famous plot from Fisher showing that with different methodology on different measurement scales, you can have permeability estimate spanning from more than 10 orders of magnitudes. So it's very poorly constrained. And that's a parameter I'm going to talk a bit more later on. So I just wanted to introduce it before ends. All right. So now if we look at what a hydrothermal system is on the ridge, that is somehow summarized by this little video. Hopefully you can see it. Really hope that the feed is working. So what you really have at the seafloor is those hydrothermal circulation, hydrothermal fluxes will affect, the biological communities around, the thermal and the rheological condition of the crust. It usually, this water percolates through high porosity faults and fractures, focusing the fluid flow in what we call discrete vent sites. It could be those black smokers, but it could also be some diffuse venting. On the way of the fluid, there is a lot of chemical reaction, changing the composition of both the fluids and the rock. And obviously, because we're talking about a very hot fluid, what you need is a source of magmatic heat beneath to drive this convection. And here we are talking about magma chambers or magmatic lenses. So that's what you see at the seafloor already. It's a chimneys with some black smokers, fractures, and diffuse fluid. And using what you see at the seafloor and any data you can collect from it, the question is a bit, what are the processes, what's happening deep down the crust? So you have to think about these systems are not being steady states. In nature, everything varies a lot. This one is very dynamical. So this temperature has been shown. The temperature is a very important, parameters because it affects surrounding seawater communities and also give you a pulse of how the system is doing. And this temperature or the velocity of the fluid here is being perturbed or changed by different processes or forcings. Of course, the first one we can think about is the ocean force. We are below, 2,000 or 2 kilometers of ocean, so you are affected by currents and tides, which will, modulate and change your hydrothermal vent temperature and velocity. So I put a lot of literature on that. It's quite well studied. And these processes are happening on what we call short time scales. So, like minutes, hour, day, months, year. And that has been, found and studied on most of the hydrothermal system we know. So that's processes occurring everywhere on this type of systems. There are other type of processes happening because we are in a very dynamical crust environment. Obviously, you have, magmatic eruptions, dikes, and earthquakes. And all of these crustal, so those ones are not periodic, those ones will be episodic forces. They will also affect and modulate the hydrothermal, outputs. There is a famous paper here at EPR that was published in 1998, a Nature paper, that was showing that after a swarm of earthquake, the temperature actually raised rather quickly from, I think it's like 5 to 6 degrees Celsius before coming back to, a steady state. That was first interpreted as being a thermal cracking event, and later on was shown to actually be a diking event. So all of that is happening at the same time, but all of that is happening in short time scales. Again, hours, day, month. And the question we had us was, what's happening, on the longer time scales? And that was not really, it's not very easy to do that because we lack data for more than a decade to even more. So the whole project started with EPR 9 degree because EPR is an integrated study site for more than 30 years now. So that was, I did not start it. I was still too young to do that, but colleagues of mine started that 30 years ago and collected a lot of data and multidisciplinary observations. So as you can see here on the map, we are out of the coast of Costa Rica, 5 to 6 days transit. We are on the fast-spreading ridge, and you can see all the black triangle are hydrothermal vents. So there is many vents along the ridge. And we have collected temperatures, fluid chemistry, biological samples since 1991, as well as you can see geodetic experiments. All these pink cycle, are pressure gauge monitoring the inflation of the seafloor. We also have good seismic, where we could image the magma chamber and the fact that the magma chamber was sometimes quite shallow and sometimes deeper. So it's not flat below. There is quite of heterogeneity. And the EPR has experienced 2 previous seafloor volcanic eruptions, one in 1991 and one in 2005. So for us, it's a good site because it's happening on human time scale. Usually when you go on slow spreading, you can wait quite a long time before seeing anything happening. So we had the chance to have a lot of data, a lot of dynamical processes at play. I'm just showing you this photo of an M vent. If you see the picture in the bottom left, that was a logger that was deployed in 2004 and was recovered in 2006 after the eruption. When he was deployed, he was actually deployed at the top of a chimney, so 6 meters above the seafloor. And what you can see here is that the new magma came, the eruption came and stopped 4 centimeters below the sensor. And that's like the black layer. That was like the new eruption. So this one was saved. That's like the only data we actually have during the eruption. All the rest were, basically being eaten by the lava. So it's not that easy to get data in these systems. So what I'm going to show you now, I'm going to focus on the temperature. Temperature is a very easy parameter to measure. And here you are looking at a time series of temperature with temperature in degrees Celsius and the time from January 1990 to January 2025 from the site of Bio9 that is right in the center of all the cluster of hydrothermal sites. What you are seeing here is a raw data. It's more than 700,000 measurements, including time series, as well as punctual measurements. So we put everything together. And on the top, I put for you to locate the eruptions and what we call the event. The event are basically diking events, but non-eruptive dikes. So when you look at that, well, it was, for me, it was quite messy at the beginning and when we started to work on the project. So I had to make some assumption and try to filter a bit the data sets to basically look at what was really interesting for me to look at. Because what you look at this temperature time series, you have many processes here happening. You may have trends, you may have mixing with seawater, changing the temperature locally. You may have, as we were saying, tidal effect, earthquake, many things. So what we did is to apply a filter that were to select only the maximum temperature over time to best represent the hydrothermal fluid not being affected or mixed with seawater and other processes. So all the red square or blue square are those, selected temperature. And when you do that, what you actually see, and that was very cool for us, is that you can see so some trends now, some, very long variability of warming period, like 10 years warming period of the whole system, then an eruption, then everything is cooling down, and then warming again, and then cooling down after the eruption in 2005, 2006, then warming again to what is possibly the next eruption window. So we got that in the proposal, we got funded that and other stuff. And now we are going at sea every year for 3 years to monitor the ramping up to the next eruption and hopefully capture what's going to happen in the next couple of years. All right, but aside from that, my question was, what the heck is happening? What's controlling the temperature? I mean, we are talking about 40-degree rise to 50 degrees sometimes temperature increase and drops of more than 80 degrees. So what's the physical processes behind to explain this very long trend over 30 years? So remember about the permeability. Permeability is a very important parameter. There is a strong permeability dependence of vent temperature at the mid-ocean ridge systems. And that's summarized in these left figures here, where you can have Q is a flux, so the heat flux of the system, T is a temperature, and the permeability is shown as those lines. So how do you read that? It's not an easy one to read, but let me try to make a simpler version on the right-hand side for different fluxes. So you have fluxes, let's say that a system could be either 42 megawatt to 325 megawatt, depending on the size of the system you're looking at or the different methodology. But anyway, if you look at one of these lines at constant flux, the message is that when the permeability is dropping, so when the permeability is becoming lower, then the vent temperature is actually increasing. So you can try to think that in a physical way as the permeability is low, so the system is not letting the fluid, passing by quickly. So the fluid is slowing down, and because the fluid is slowing down, it has more time to get heated, and it gets warmer, and that's why the vent temperature is increasing. So we derive this equation linking the permeability to the temperature to the heat flux. And we apply that to our system here. So what you see on the top side, that's the same plot as I showed you previously. It's a bit customized, but that's basically looking at the ramping, so increasing of temperature in red and cooling temperature in blue over time. We could extract the rate of it, 2.5 degree per year warming to 3 degree per year warming. And we derive from this temperature and the expression I've shown you before, we derive the permeability of the system. So basically, when the fluid is getting warmer, the permeability is dropping and vice versa. So now we have this permeability change of the system. Is how do you explain the whole permeability of the system to change, all right? And a mechanism is the overpressure. Basically, if you put the system in compression, then the permeability will shut down and the fluid will rise. So we use another expression that links the permeability to the overpressure in the crust, and that's exponential law, to derive now what would be the overpressure, the compression in the crust to explain this change in permeability and temperature. And we end up with an overpressure rate of 0.38 to 0.4 megapascal per year for those trends of warming temperature. But again, is that even something possible? How do you compress? How do you overpressurize your system by this amount at the ridge? So luckily for us, you remember, we have a multidisciplinary data set thanks to many PIs and collaboration. And we had geodetic experiments. What's a geodetic experiment is like geodesy. On land, you do that with a GPS, and that's all great. Underwater, it doesn't work. So we use, for vertical motion, pressure gauges to record the inflation of the seafloor. So we had a line of pressure gauges coming by the sites of Bio 9, so the same sites that you were looking at the temperature. And that's all those dots here. So we can monitor the inflation rate of the seafloor, and that's what you see here. Then we use an elastic model to best fit this data. And we extracted from the model what would be the pressure changes due to the inflation of a magma chamber. Let's say that your magma chamber is inflating. How much of this inflation is going to overpressurize your system? And that's what you see in the bottom plot with color from blue to red. If you were to take, now if you are going to look at the axis and you take an average profile of that, that's what you see on the right hand side. So depth from seafloor to the magma chamber, 1.5 kilometers below, and that's the pressure rate. If you take the average of this column here, because we are working in one dimension in this temperature permeability model, then you would end up with an average of 0.33 megapascal per year constrained from an independent data set of seafloor uplift data. And that's actually a very good agreement with our value of 0.38 Pascal that was estimated, if you remember, from deriving things from temperature only of vents. So, I will wrap up later. I will just add before that a note, like 2 layers of what we're observing. As I told you, first, we have several sites. So one of you might wonder, what's going on to the other sites. So that's what's going on. We have basically monitoring 10 kilometers of a ridge, which is quite a segment. And all the vent fields show the same things, which was incredible. Everything is warming up between eruptions, then an eruption, everything is cooling, then warming up, and so on. But they are all doing the same with a different rate. They don't warm up the same way and they don't cool the same way. And that's quite interesting as well. Probably is because of the heterogeneity in the permeability field, the fact that the magma chamber is not flat. Remember, there is like shallow part and deeper part. So not everything is being overpressurized the same way. Not everything is being modulated the same way in terms of absolute values. And finally, I will finish on this strontium isotope. So that's another type of measurements we have, independent as well. So chemistry is not really my thing. So I'll try to not say like too crappy things and try to make a good case of these slides. But basically, we're looking at this strontium isotope signature ratio. There are two sources for strontium, either like seawater driven as an end member or either basalts driven as an end member. So if you monitor this ratio over time, you can have an idea of, somehow how much it is affected by seawater versus how much it is, from the end member of basalts. What we see here is that after an eruption, following an eruption, the strontium ratio actually shifts very much toward the seawater. And between eruption, sorry, someone say something? No?
Only 1 minute, please.
Yeah, this is my last slide, and then I'm done. So basically what you have is you can record the change of permeability of the system. After an eruption, permeability increase as shown by the temperature. Then you have more seawater, then the strontium ratio is increasing, and vice versa in between eruptions. So that was very nice to see. So finally, and I will leave you on that, this is a summary slide. So we were, for the first time, put in evidence this multi-decadal variability in the system controlled by the inflation of magmatic chamber that is impacting the permeability field of the entire vent field. We show behavior for what it's between eruption, like a slow inflation, versus a rapid deflation after the eruptions. And of course, opening question for deep sea ecosystem, what's happening on those timescales for the ecosystems. I would like to thank you very much, and I'll finish with this beautiful picture we took last year. And I hope that the connection was okay and that you enjoyed it. Thanks.
Thank you. The video and the image and the videos about black smokers are amazing. I love them. So I enjoyed very much your presentation. Thank you very much.
Yeah, thanks.
I'm sure that there will be some questions later, so I hope you can stay with us. Or
I'll stay a bit. And otherwise, feel free to drop me an email. I'm super happy. I'll try to stay, yes, for the Q&A, of course.
Thank you very much, Thibaut. All right. I'm now going to speaker Pablo González. He is also a friend of mine. We started our research, our career more or less at the same time. I'm a bit earlier, but but we start in the same institute. We have work in different places. We are researching in different topics, both related with volcanism and volcanic islands. But now we are working again together at the Spanish Research Council, so it's great. Pablo is an associate researcher, professor in the Department of Life and Earth Sciences at IPNA-CSIC here in Tenerife. He leads the volcanology research group at this institute and represents the Spanish Research Council at Scientific Advisory Group for the Canary Islands Volcano Risk Emergency Plan. In 2020, he received the Leonardo Award from the VVA Foundation that recognizes annually the 50 most promising mid-career researchers across all sciences and cultural disciplines in Spain, so congratulations. For over 20 years, Pablo has maintained an excellent reputation recognized for his professional collegiality and outstanding research, teaching, and graduate supervision. Pablo is going to go over the pre-co and post-eruptive volcano deformation at Cumbre Vieja. It's a really interesting topic, and so the floor is yours, Pablo. Thank you.
Okay, I think now. Thanks to the organizer first for this invite talk and the nice work from Inés. Of course, we know from many, many years, and I consider myself mentored by her when I started. So it was very supported when we were only 3 geologists in the institute we started. So yeah, thanks. Let me see if I can move. It's not moving forward. Oh yeah, now. As Eugenio started his presentation, when you do a lot of research, you need a large team that help you to achieve some of the very, unravel some of the complexities that you want to study. So this presentation is in fact putting together a very large team that has been focused to try to understand what we can learn from pre-eruptive deformation, co-eruptive deformation, and post-eruptive deformation for assessment, scientific assessment, and also for understanding better the magmatic systems in the Canary Islands. So let's go first. The core challenge, and actually what drives most of my research, is trying to develop, which is very, very ambitious, I know, but I would like to do baby steps towards it, is to create more predictive, powerfully predictive models of volcanic behavior. And of course, there are very well-known tools like long-term monitoring, like say geology, age of rocks, documents. And we have very good success in the past of these methods. For example, this book is about a geological survey of United States that was published only a few years before the Mount St. Helens eruption. And the key to obtain a predicted framework scenarios of what the volcano could do in the future was in the geological record. So in these layers of pumice that will be maybe in a cut of a road, and you will not pay too much attention, but if you look in detail, it can tell you what is capable a volcano. So the American scientists related to what they knew at that time. There was the Mont Pelée crisis in the beginning of the 20th century that killed thousands of people. And then this was a valid forecast, obviously not in real time, but a valid forecast for what it could come. In terms of medium to short term, our best ally is the volcano monitoring tools, and I will not go over all of them, but I would like to say that our best understanding of how to forecast volcanic and eruptive activity is based on these tools and conceptual models like the volcanoes that behaves like a closed systems, semi-open, and open systems. The Canary Islands fall into the closed systems. That makes us very fortunate because a closed system produces very large pre-eruptive signals, either deformation, seismicity, gas release. The drawback of this behavior is that we depend on crises to learn. So we have a very, very sparse record of what a volcano is capable or what the precursors are telling you about the future. So this is the context on which, with a tool that is mainly used for volcano monitoring, I will try to make advances in science and research. What are my focus? Volcano deformation and Thibaut. I thought at the beginning that I was going to be like the outlier in this seminar about submarine volcanism, but he rightly pointed what I was going to tell in this slide. So a closed volcano system can be conceptualized as a system that is recharged with magma over a certain and uncertain period of time. That could be short, years, centuries, decades, or very short, that release this magma storage in eruptions. And in terms of volcano deformation, what we usually see is like cyclic behavior, in the same way that Thibaut was mentioning about the evolution of temperature. So many different and contradictory information could be revealing a common pattern. And this is very good news, because if we combine different methods, when one tool is not working, maybe other can supplement. So what I'm trying to say is that if we study volcano deformation, we can follow and track the magma accumulated in a system, ideally. Obviously, not always is the same. Can you play the... So what are the tools at our disposal for volcano deformation? Nowadays is mainly satellite radar interferometry, satellites that measure and pinpoint radar signals that bounce on the surface and then return to the satellite. And as you can see in the animation, a satellite is orbiting constantly the Earth, and due to the rotation of the Earth, you revisit the same place every few number of days. In this particular configuration, every 6 days. Which means that every 6 days, you can point this radar signal, get the bounce, and then compare and see if the delay has occurred or not. These satellites orbit around a height of 800 kilometers. And to give you a scale, we are able to measure phase differences in the radar signal in the order of a couple of centimeters. So every pass, every 6 days, we can control the change in elevation in about 1 centimeter. And then if you average over time, you can get into the millimeter of motion. Another very well-known tool that gives us precisions even better, but in a sparse location, is GNSS, like a GPS for most of the people. So those tools were available to us to understand the beginning of the eruption. Unfortunately, very, very fortunately, the onset of seismicity and the deformation was consistent with an impending eruption. A forecast was able to do, and the alert was given, and the population was ready for an uncertain but very likely eruption to start. So the precursor scales, the deformation scale and the onset of seismicity, was in the order of a week. So here what we see is a busy plot on which we can see the period that is more interesting in this part of the talk, about the month of September and the beginning of October, on which I would like not only to highlight the onset of the eruption, but also the change in volcanic products. For the first few days, tephrite, which is a high silica contained volbate magma, was erupting. And that certainly around the 27th, 28th of September start to change to more primitive composition, basanite. So this has been reported clearly, identified. The geologists say that this was occurring, but we don't know exactly why it happened and how it happened. So my goal in this is to combine and use all the satellite acquisitions that are those dots in the top of the image say, many different satellites were acquiring data in every of these dates, and try to combine this information to see if something has changed in the way that the magma was progressing towards the surface. This is a bit technical slide in the sense that what we obtain, or what we see in the top left panel, those two panels here, is the observations. Let's say the observation is indicating like a bull-eye pattern that is saying that the ground was moving up. That motion towards the satellite can be modeled with some mechanical analytical expressions that you can combine. You know, for example, here we can put a small dike that opens and then a magma reservoir that was inflating. If you see, the combination of these two sources explain the observations more or less well, so that the residual is low. When we are happy with this process, which is very tedious and it takes a lot of time and is more complex than what I just told you, what we obtain is some kind of a idealized geometry of where the magma could have been. And then is the moment on which we can start to use all the satellite data that we acquired to start to see which part of the magmatic system was opening at different times. So, and this is the way that we agree with other researchers. This is not new. You know, we know that the magma accumulated in the western flank of the island around 4 to 6 kilometer depths, and then make its way in a lateral motion, you know, a bit inclined toward the sea, to reach the surface in a set of dikes, probably more than one, because even this group identifies several sub-segments. So this is a very small figures, but they say that we resolve it. I show you the data is here. So what we do, every single of this panel indicate the time difference between 2 days acquired by the satellite. But this is not the way that the human usually see evolution with time. What we want is a time series. We want every day, not the difference between days, but every day a parameter that can follow. This is in turn solving what is called a linear model. So the combination of all this information can be solved linearly to obtain a time series. It means what happened in this day, what happened this day, and follow on. So this is very small, but I would like to make like an animation here. So what you see at the top is the difference in opening between 2 consecutive days. So it's like saying in a snapshot what the time series of opening of dikes and seals were occurring. And on the right panel at the top, what we see is the total amount of magma in place in seals and dikes that reach the surface. I know that maybe it's a bit too busy, but what I would like to highlight and strengthen is that there is what we already knew, that there was magma accumulation on the western flank at around 4 kilometers depth, and then some kind of conduit that goes all the way to the summit where the volcano erupted. But here, if you pay attention, there is, the data requires some opening to occur in a much more straight line. And this, if you will be able to be superhuman and see all the different numbers, you will see that this occurred in late September, early October. So what are the main conclusions or what we think is happening? So that the onset of the seismicity and deformations show that there is a small difference in space and time patterns, a little bit more complex that is already been said, and that in late September and early October, the data hints that there was a more complex magma conduit system than what we already have been published, with a magma that may have go more straight from a reservoir around 10 or 15 kilometers depth all the way to the summit, coinciding with the change in from tephrite to basanite. So the second, what happened during the eruption? So as soon as the eruption starts, the next question that everybody was telling us is, you can see, it's the 28th of September, the 20th of September, the 20th of September, how long is going the eruption? So I say, the people was eager to know the future, and this is the big challenge for volcanology. sometimes the best information we have is the geological and history record. This is the knowledge that we had at that time. So we know that Cumbre Vieja eruption lasts in the historical record from 24 to 84 days. Is that true? We don't know. You know, it's a good indication, but no one will tell you it's going to last 64 days with this, plus, minus, whatever. So what we want is something more quantitative and something that we can update with time. So what could be used? For example, daily seismicity rates. And as you can see here, the seismicity rates that the monitoring agency was recording indicating a peak around late October and then start a monotonic decrease. But what happens when you think you start to understand something, that the volcano does something to screw you up? So I remember, because we were in a Menendez-Pelayo course, the day we start to think, oh, maybe the things are calming down. I heard that the meetings to assess will be going to be only every 2 days. So no, the seismicity pick up. We don't know what is going on. It's only other vents will go up. Another good indication will be the total mass of SO2 or the fluxes, which will be even better, but fluxes are very, very difficult to calculate. But you can see that it's a very messy and very noisy time series. So it's not really something that definitively this is going to end now. No. What? Every master has his own expertise, and I will go and say, put the pike on my technique, right? I understand more the formation, the mechanics of volcano, and I say, so as you can see, the formation can also tell you about how it's deflating, how much or how rapidly magma is evacuated from reservoirs. So in the case of La Palma, the Geographical Institute of Spain has a very dense network that was indicating by around the day 30, 40 of the eruption that the volcano was start to contract very clearly. Those arrows are indicating that you are moving inwards, and this indicates that you are contracting. This contraction was more or less consistent with a source that was losing pressure at around 10 to 15 kilometer depth. As you can see, the vertical components are also pointing down. So the things are losing pressure. So now, if you look instead of the spatial pattern, the temporal pattern, you will see that the distance between the Mazo station and La Palma 1, that is in Fuencaliente, that is more or less at the same distance from the pressure that was losing, the source that was losing pressure, indicated a decrease in pressure. So it was shortening. This going down means shortening. Sorry if the scale is a bit confusing, but going down is shortening. And as you can see, if you take a window of 38 days, you could fit an exponential decay that was flattening over time. This is the caveat. If you assume that the deformation, when it goes to 0, means that you stop taking pressure out of the system, you will probably think that the eruption could end. That will be only true if there will be no recharges in the system. What did happen later? As you can see, when it evolved, the deformation recorded was having some up and downs that we think they are real, and the model that we could forecast it in the day 38 start to deviate. But at the end of the day, it was not significantly different to make the forecast window totally invalid. So what we have done after that is to repeat with every single day if that will have been possible and when it could have been possible if an eruption of the same characteristic will happen in the future in La Palma. So what we were able to do is say that the forecast will be possible around the day 40, as we did it, but that coincides with a parameter called twice the tau, the relaxation time of the system. A second thing that we confirmed is that because there is a linear relationship between the volume eruptive and the shortening of and the change in pressure, we can, with high confidence, say that there was almost no or very minimal deep recharge in the reservoir at 10 to 15 kilometers. And this is something that we would like to debate with the rest of the community, because there are contradictory informations about that. But this is, from our perspective, less questionable. So the fact that the pressure has decreased to the level of 2 to 3% of the previous pressurization of the system opened the question that is if this is going to be the same in the future, and if it has any means to be a general method. So finally, what happened after the eruption finished? Well, the eruption has, in La Palma, produced a very large lava flow field that is very interesting for many different aspects. And one of them is that this system will be very hot and very cooling down for many years. So, just to go directly and save some time, what we are saying is that we could use these satellite images from different orbital passes that detect the amount of compaction that the lava flow field has suffered since December, since the eruption ended. And these measurements that we are presenting here goes until the 6th of June, and it was done in the context of a master's degree in Granada University by Andrea Garmendia. So what we see here is two lineups and maps that they are not exactly the vertical motion. We have to do some operations to obtain like a purely vertical compaction of the lava flow field. As you can see, the amount of deformation, compaction that has occurred in the center of the lava flow field is more than 1 meter so far. That's not a stop. It will continue in the future, but maybe at a lower rate. What we can see is clearly that the lava flow thickness is correlated with the amount of deformation recorded. This is not surprising. You know, the more volume you have, the more you can contract. And what we have seen is that the temporal evolution indicates that the process is decaying over time. So except, you know, some places that are still very, very strong, that is in the center of the lava flow field. So now essentially, as you can see, where it was the LP2 before the eruption, that's essentially where the strongest deformation is occurring. So has this have any predictive power? Well, this context, there is not an eruption impending, so this deformation is not informing us about anything related to the deep system, but it could be relevant in the sense that we are in the moment in a recovery phase. And this knowledge could inform the authorities to see whether or not they have to budget repairs or delay some of the constructions or find better routes for roads in the future. Because so far, if we only take into account the deformation occurred since the inauguration of the road to June 2024, we can see that many segments of the lava flow field has been subsiding around 12 centimeters. In particular, in an area that our colleagues from the Geological Survey know very well, the Pahoehoe field, is where we have the strongest affected section with areas that start to suffer deformation, very strong deformation in the road, and reported in August. So what we say from this section, so that the post-emplacement of lava flow show a strong compaction. This is not surprising. I didn't show up, but when we decompose into vertical, we can do also with the horizontal. And there is a bit of west motion creep next to the bends, the main bends, but this is not clear in other part of the lava flow field. So I leave here the conclusion, saying that the pre-eruptive deformation reveals that the magma system was a bit more complex, particularly between the beginning of the eruption and early October, when we have the changing magma composition. The real-time interpretation of co-eruptive deformation may be useful for predicting the end of eruptions. We have to keep testing for sure. And that the INSAR data, the satellite images after the eruption, could be used for monitoring or enhancing the monitoring system that can be done in the ground for the infrastructures that could be used or construct on top of lava flow fields. Thank you very much.
Thank you, Pablo. The volcano has been and is a natural laboratory and is giving some interesting research like Pablo has shown. Well, the last talk before the coffee break is in charge of Ulf Skyllberg. He is professor in geochemistry, Swedish University of Agricultural Sciences. He teaches and conducts research in environmental geochemistry and soil biogeochemistry. Yeah. A red thread in his research is the role played by natural organic matter in acid-base reactions and in the geochemistry of metals and organic pollutants in soils and waters. The last 20 years, his research has been much focused on mercury biogeochemistry, and he's going to talk about this topic today. So the floor is yours. Thank you.
Thank you. Thank you very much for the nice introduction. First of all, I would like to thank Eugenio for inviting me to give this talk about something completely different, I guess, for most of you. It's an element which we expect is very much affected by the environment close to these submarine volcanoes. And it's the element of mercury, which I've been studying for 30 years around by now. So I would like to give you some type of overview of what I expect might happen with mercury in the vicinity of these kind of submarine volcano environments based on my experiences on the biochemistry of mercury in other types of environments. I've not studied these environments at all before, but I studied mercury biochemistry in soils, wetlands, lakes, and so forth, terrestrial environments. Let's see. So that was my topic then. I tried to touch a little bit upon these submarine environments, what we expect when it comes to mercury biochemistry. So first of all, why is mercury a problem in marine environments? We know that the concentration of mercury in the atmosphere has increased by 3 to 5 times since the industrial era because of human activities. It's mainly then fossil fuel combustion that increases the mercury in the atmosphere, and of course also in terrestrial environments and marine environments. And that's because mercury has an elemental form that is gaseous. So mercury can stay in the atmosphere for months, or maybe up to a year, and can spread all over the globe before it's deposited back into the environment, marine or terrestrial environment. And then we know that we also have natural sources, and volcanoes are considered the most abundant natural sources of mercury. And I also learned, preparing a little bit for this conference, that the submarine volcanoes are actually the most numerous ones. And therefore we expect these sources to be very important for mercury, especially in the marine environment, of course, but also for the globe as a whole. The most concern about mercury is the formation of a very toxic form of mercury. It's called methyl mercury. It's a methyl group. Sitting on the mercury molecule. It's formed by the action of anaerobic bacteria from inorganic mercury, and it's biomagnifying in food webs. It's very toxic. And we know that, for instance, in marine environments, tuna fish, sharks, predator fish have very high concentrations, especially locally, of mercury. Of this, especially this methyl mercury form. So it is the methyl mercury form that really magnifies in organisms. And we know also that some human populations living mostly on seafood are affected by mercury, really. The development of the neurological system of children is affected. So just to repeat a little bit, the fundamentals of mercury. So we have the gaseous phase of mercury, making it widespread over the globe. It can be the elemental mercury can be in gas phase, but also in liquid phase. And then we have the most abundant form of mercury in the environment, that's inorganic mercury, with oxidation number 2. And then we have the organic forms, the methyl mercury I talked about, which is much of the focus in mercury biochemistry research, is the methyl mercury. We also have dimethyl mercury, especially in marine environments, and its source is kind of unknown. So it's quite a lot of dimethyl mercury at some depths in the oceans. In sediments, the concentration of inorganic mercury is about 100 times or so higher than methyl mercury, but in waters, the methyl mercury concentration can be pretty high. So that's a concern, and that's why it's taken up in the food web as well. Obviously, some major biochemical processes is then the reduction of mercury 2 to mercury 0, losing the oxidation state from 2 to 0, and also the back reaction to oxidation. And then this process of methylation is very central in mercury biochemistry research, how inorganic mercury and also elemental mercury can transform to this very toxic form of methyl mercury, which is taken up then in the food web. And then we have the reverse process also of demethylation. So in this kind of chart you might have seen, you can see all these processes taking place. In this case, it's more of a freshwater ecosystem, but it's the same kind of reactions taking place in marine environments. So we have the emission and transport and deposition of mercury 0 and also the mercury 2 deposition. And then we can have the methylation process forming methyl mercury. The methyl mercury is taken up in the food web. You can have methylation also in the sediments. And you can have degradation of methyl mercury in the sediments to inorganic mercury. The major degradation process of methyl mercury is then the photodegradation process. That's the major process, both in marine environments and also in freshwater environments. By far the biggest sink of methyl mercury. And then we have the oxidation reduction processes. So in mercury research, most focus is on the net formation then of this methyl mercury form. And it's then the change of methyl mercury over time is then contributed by methylation process, this demethylation, and you can have mass transportation processes as well. So I will kind of focus on the methyl mercury and how can we expect methyl mercury to form in connection to these underwater volcanoes, for instance. First of all, we need to look at the fundamentals of the chemistry of both the inorganic mercury and the methyl mercury, and how these forms of mercury bind into different components here. I will look at that first. And here organic matter is important. And then I will look into two different conditions with, here, where we can look at how these forms then are bioavailable for this methylation process to turn in inorganic mercury to methyl mercury, and the role of natural organic matter under sulfidic conditions, which we can expect. I learned a lot about this Eugenio's summary here of what really changed when it comes to chemistry with the Tagoro eruption there, and it is crazy changes. And also you saw the sulfide there down to 100 micromolars or something like that. So it's very relevant to think about sulfidic conditions and also non-sulfidic conditions. This process is very important for the degradation of methyl mercury, the photo-degradation process, but today I don't touch upon that. I don't have time for that, so I kind of concentrate on these things here. So we know from studies long back in time that mercury and natural organic matter goes hand in hand very strongly. And this is a well-known historic study where there's concentration of inorganic mercury, black dots, are measured together with the color of a stream. This is a forest, small forest stream. The color is basically natural organic matter. So you can see the pattern of mercury and natural organic matter follow each other very carefully, strongly, strong correlation. And why is that? Well, the reason for that is that mercury binds to natural organic matter and to certain groups of natural organic matter. Mercury is a soft metal, and therefore it binds to soft ligands. And the soft ligands in natural organic matter is sulfur groups. So studies have shown then that mercury is binding to sulfur groups in this fashion. 2 sulfur groups, this is a kind of a particulate or dissolved natural organic matter, you see the sulfur groups. And these sulfur groups are called thiols, thiol groups, reduced sulfur groups. So mercury is a soft metal, likes the very soft element sulfur, which we also find in natural organic matter. So this is the structure you find in natural organic matter if you have kind of equilibrium in the system that is, stable system. You can also have actually interactions with other sulfur atoms a little bit further distance here. Methyl mercury is the same. Here is the methyl mercury molecule. You have the mercury and the carbon, and then mercury is also associated with sulfur groups in natural organic matter. So natural organic matter is a very key component when it comes to mercury biochemistry, both for methyl mercury and inorganic mercury, binding to these forms. So what happens then if we go into sulfidic conditions? So then we have the thiols we talked about just, but we also have inorganic sulfur. Obviously, we have a lot of those inorganic sulfur in connection to submarine volcanoes under certain conditions, I guess, depending on whether we have oxidative conditions or reductive conditions. And it's been studied quite a lot. The last, I would say, 20 years, it's been a focus on the formation of something called mercury sulfur clusters or nanoparticles of mercury sulfide. So mercury, if you have inorganic sulfur present, will form clusters or polymers of mercury and inorganic sulfide components. And if we don't have any natural organic matter in the system, these clusters very quickly will turn into a crystalline mineral of mercury sulfur. It's called metacinnabar. And this form of mercury is not so available for methylation, for instance, so it has a low availability. But if you have, at the same time, you have the thiol groups of natural organic matter present in the system, these natural organic matter components will stabilize these clusters. And these clusters are much more available for methylation than the crystalline mineral. So this is a kind of kinetic process. We're talking a time-dependent process where the clusters over time age and change its solubility, it's decreasing, and the bioavailability goes down, and then we get the metacinnabar. And here we have the bacteria that methylates mercury. So the turning of inorganic mercury to methyl mercury is through bacteria. So the anaerobic bacteria takes up the inorganic mercury, and inside the cell of these bacteria, anaerobic bacteria, which I'm sure you have a lot of in the connection to the hydrothermal vents, for instance, the mercury is turned into methyl mercury by an accidental process within this bacteria. But then the availability of these clusters stabilized by natural organic matter is much more available for this methylation process than the metacinnabar. So this is something to look into, for instance. What's the conditions then over time, maybe also, and over distance to these submarine environments, submarine volcanoes? We made an experiment to test this at some point. We added different types of forms of mercury to anaerobic bacteria in a anoxic sediment. So we looked at an anoxic estuarine sediment, and we used the stable isotopes of mercury. Mercury has 6 stable isotopes. You can use them to label different types of mercury species. So we added, in this case, 5 different mercury species, and looked at the rate at which they were methylated by these bacteria. So this is the rate of methyl mercury formation. And we can see these crystalline materials, they are not very quickly turned into methyl mercury. If you add mercury together with iron sulfide, which I understand also would be a very important component in close connection to these submarine environments, you had a lot of iron 2, you had a lot of sulfur, for sure you will form this mineral, McKenna white, iron sulfide. If you add mercury to iron sulfide, you get a reaction. And initially, after 1 day of reaction, this form of mercury is quite available for methylation, for uptake by these anaerobic bacteria and turning into methyl mercury. But if you have aging for 24 days, you can see the rate of methyl mercury formation goes down. And it now is actually very similar to these crystalline minerals. So you have an aging effect here where mercury is less available over time. Here we have mercury bound to the thiol groups in natural organic matter I showed you in the beginning, and you can see the availability is much higher. The highest availability is, of course, if you add just mercury nitrate in solution to this system, then the mercury will be very much available in the beginning, and then every time you have this aging process in the sediment as well. So that's very highly available form of mercury. So then we have some studies also conducted under non-sulfidic conditions. What's going on then over time if you don't have this maybe thermodynamically stable mercury 2 complex I showed you in the beginning. And then I just want to show a study here. This was done 10 years ago, but it's still kind of not solved what's going on here. It's a Canadian group. They added mercury together with natural organic matter. You can see here increasing concentrations of natural organic matter here. And they then measured the bioluminescence of a certain bacteria that which indicates the uptake of mercury. This bacteria gives radiate light when the mercury is taken up. So uptake of mercury here along this axis by the bacteria. If you add mercury and NOM together first and let it kind of equilibrate first, and then you add more and more organic matter, you can see the uptake of mercury goes down. So that's the kind of general historical view of uptake of mercury, that natural organic matter actually decreases the uptake of mercury by kind of stabilizing the mercury, and it doesn't take up by the bacteria. But in this experiment, they did not do this pre-equilibration. They added the mercury and the natural organic matter at the same time. And then actually they get this pattern that if you increase the concentration of mercury, actually that increases the uptake, the availability of mercury for a certain concentration of natural organic matter up to here. And then by adding more organic matter, the uptake was decreasing. So we have some dynamics in the bioavailability here. And the hypothesis of these authors, they hypothesize that we have 2 types of organic matter. Some organic matter, I would guess smaller molecules, are more bioavailable. It makes the mercury more bioavailable for the uptake of bacteria. So in the beginning, when you add the mercury, it binds to some type of fraction of organic matter. You know, organic matter is a very heterogeneous composition of small molecules and large molecules. So I would guess these are small molecules, and they make the mercury available for the bacteria to take up the mercury and methylate it. But with time, the mercury moves from these DOM1 then to DOM2, which is another type of organic component. Of course, you have large molecules also in organic matter. I would expect these are larger molecules. And those are not taken up by the bacteria. So you have some pattern here where in the beginning, the mercury bonded to the small molecules can be very much bioavailable, but with time, mercury migrates into larger, more recalcitrant, bigger molecules that are not bioavailable for uptake and methylation. So to summarize a little bit from that study and what we have also seen in other studies, this is kind of the kind of pattern we kind of working on now. We have a system where we either in experiments add mercury, or mercury is deposited in natural environments, or we have redox events in natural environments. Once the mercury finds the organic matter, it first, within seconds, finds the small molecules. Like this is the low molecular mass thiols. Here we have thiols together with oxygen groups. Even the chloride ions play a role here. And of course, in marine environments, we have a lot of chloride. So it's a kind of kinetic process here, time-dependent process where mercury moves from small molecules in natural organic matter, also involving chloride in the beginning, to, with time, larger molecules. And over time, then, the mercury gets less and less bioavailable for uptake of these methylating bacteria, and therefore we have less methyl mercury formed over time. Yeah. So, and pH is a factor here as well, and it was very interesting to see that it was very low pH in connection to these eruptions. So, actually enhances the influence of chloride in the system. So within minutes, the mercury is moving from the smaller molecules and also forming these mixed complexes with chloride and thiols, and then into minutes, hours to days, moves into the larger fractions of organic matter, making it less and less bioavailable. So, and this is a kind of redox, this is kind of a wheel which starts all over again with new, if you do experiments or with no depositions or you have redox events. And I would also guess if you have an episodic input from submarine volcanoes, you will start all over this process. So, to conclude, what's going on in connection to submarine volcanoes? Well, how is the mercury sitting? Is it sitting on natural organic matter like this? Is it sitting on natural organic matter together with chloride like this? Is it forming nanoclusters if you have sulfidic conditions or nanoparticles? That's a good question mark, and I will join the cruise with Eugenio pretty soon, and we will, together with also with Andrea Garcia, we will hopefully get some answers about this. What is the chemical composition of mercury in connection to these volcanoes, and what happens when it comes to methylation? Thank you.
Thank you. I have never thought about mercury and volcanoes, so it's amazing. Please, I think that all the speakers can join us here.
Yes, thank you very much. I know everybody is keen for a coffee, but I would like to just have a very small session of questions and answers to allow people to ask questions. If the speakers could gather on the podium so that I can nab you easily, that would be great. Thank you very much to Eugenio, to Thibaut, to Ulf, to Pablo for those really interesting talks. I would like to give priority, if possible, to anybody who's joining us online. If you'd like to ask a question or make a comment, please put it in the chat, because you won't be in the coffee room with us, unfortunately. Remember to give us your name and let us know where you're from, so we know who you are. And Alba will let me know, and we can read out any questions. But whilst they do that, is there anybody in the room who'd like to ask a question? Ooh, you can notice the lack of coffee this morning. Don't be shy. Yes, so we have Adriana with us. Adriana is one of our marine science students. Thanks to Eugenio and the collaboration that we have together, we have a month-long program, training program here in the Canary Islands. We have 2 students here who will hear throughout the day. Ram, I know I'll be coming to you as well. And they'll be joining Eugenio later in the month after some training with us first. So Adriana, if you'd like to tell us your name, where you're from, and pose your question, that'd be fantastic. Thank you.
Thank you so much. My name is Adriana Lisa Pardo. I'm from Colombia. I just finished my master in University of Texas at San Antonio. And I'm so happy and excited about this opportunity that is coming this month. I have a couple of questions. One is for Eugenio. Was not very clear to me about how is the recolonization of the ecosystem after the eruption, if you do any activity with the with the animals or planktons, or they just go back by themselves to the new ecosystem after yeah, all of these gases and new material.
Well, this is a really good question. Me acaba de preguntar que cómo es el proceso de recolonización en el volcán del Hierro, si es que ha venido de manera directa o no. Y the question is that at the beginning, during the first 6 months of the eruption the volcano was emitting a huge quantity of heat, gases, and everything. That the condition, the perturbation was really, really high. So the life over there was impossible. But after that, after these 6 months, the anomaly was reducing quite a lot. So the life could grow, and also because the submarine volcano is located close to the marine reserve protected area, so all the natural fishes and everything was transporting to the volcano, no? So in the marine life, the only thing that you need is a substrate, is the rock, no? And later, because all the nutrients and everything, the components are in the water. It's completely different to the recolonization in the surface, no? That take more time, years, and even centuries. But in the water column, we have already seen that just in the few years, the recolonization process is really, really fast. So after the eruption of El Hierro, just in 2 years later, all the new lava was completely recovered with new algae, everything, and now also the whole water column are completely recovered. So I always say that you don't need a GPS to localize the submarine volcano of Tagoro over from the surface, because you will see always a shipping boat just over the volcano fishing over there. So you can see that is a big oasis of life.
Thank you, Eugenio. That's fantastic. In fact, I think we went on the boat with you just a few weeks after the eruption in La Palma. You were bringing up samples, and already you could see samples of indications of this recolonization. I mean, it's incredible. Nature is amazing and far wiser than we ever will be, I think. Any more questions from the floor before we go for coffee? Javi, yes.
Thank you. I'm Javier Díaz Cabrera. I'm from Gran Canaria, and I will be doing a presentation later. But I had a question for Pablo, because obviously when you have a volcanic eruption, you have a massive disturbance. So I wanted to clarify what change did you see in the formation? Because obviously you had, when you changed from magma type, you had this original deformation from this first batch of magma. So during this eruption, where you already had such a big disturbance, how were you able to see the change in deformation? Like, was it a change in deformation throughout the system, only localized above the new batch of magma? So how was this change?
So the way, thanks for the question. I think it's a consequence of me being not very clear how we find out the magma underground. So the way that we discover the magma pathways or where it's stored is based on models that best fit observations. What those observations are is the pattern of uplift, is how big and how elongated or how concentrated is the pattern and the area of the deformation is indicative of the depth and the geometry of the magma storage source. So when we say that this later, after the eruption started, we find evidence of some of our data sources to indicate that there is magma there, is because they have some anomalies, some areas of uplift that are consistent with magma in a different place than before. So, and they do not share the same area of deformation and the same pattern. And that's why we are confident that there are different magma source storage regions. When you walk on the field, it's very difficult to see these changes by your naked eye. So most of the deformation happen without noticing. except if it's very localized, very concentrated, as it happens during bent fissure areas or cracks that open with deformation localized. But most of it is we rely on these instruments to really measure the deformation. Otherwise, we will not be able to see it or estimate.
Thank you, Pablo. Any more questions? Yes. Scott, hang on.
Thank you. I'm Scott Waters from Pisces 6 Submarine, and my question's for Thibaut. So I sent Bruce a message, even though it's the middle of the night, and he was really excited to see that you were speaking. And my question is, what was the main reason for using a human-occupied vehicle, the Alvin, and what is one capability that you wish that you can add on that expedition?
We can't hear you.
We
sorry.
cannot hear you.
We can't hear you, Thibaut. Can you put your microphone on, please? We can't hear you. No. No, we can't hear you. I'm sorry. No. Maybe it's because you have your headphones in. Maybe if you speak directly. We can't hear you, I'm sorry.
In a bit time, I would like to ask a question also to
Okay, let's try and sort out your sound issues. And in the meantime, I think Eugenio is going to dive in with a question with Ulf while you try and sort out your sound issues with Alba. Thank you.
Yeah, Ulf, I've got a question for you. It's a really interesting talk. Thank you so much for coming here, and thank you so much for participating in the cruise. But I would like you to express how important to measurement the mercury is in the submarine volcano, and what is your expectation? What do you think that you are going to find in the submarine volcano Tauro? I know.
Okay. Well, before coming here, or 2 days ago, I made a search on the internet on how much. Previous studies on Mercury and submarine volcanoes, and very few, I think. And the one I saw, it was quite enhanced concentrations of mercury, and they kind of sampled the organic matter in the water and then measured the mercury. So it's really enhanced levels. And I'm thinking about what you can do is actually take some of these samples together with the mercury and actually go to some of these sources. We use synchrotron radiation. And you can basically measure directly on the samples the speciation of the mercury. So it would be very interesting to see whether it's similar. I expect it to sit on the fire groups, as I said, on natural organic matter, but we have this time-dependent reaction with chloride, which I think is very interesting, and especially if you have this lowered pH, you talk about several pH units below 7, then the chloride will be more competitive. So it would be very interesting to look at that. So thanks.
Thank you. Thibaut, can we hear you now? Try again. I think you wrote the answer. We still can't hear you, I'm sorry, but I think you put it in the chat, so I'm just going to pass the microphone to Alba. Just 1 second.
Yes, here's the answer. The first reason is availability. We have used JSON for our first cruise, for example, but it turned out to be much more efficient to use Alvin for the precision work of sampling fluid and deploying loggers. Also, we couple it with the use of Sentry at night for mapping. I hope that answers your question. Thank you, Thibaut, and sorry for the inconvenience.
Thank you, Thibaut. I'm sorry. No, we still can't hear you. I'm sorry. Any more questions from the floor? No, I think everybody's keen for coffee. I just wanted to leave you with one final thought, because everybody says to me, why do you keep talking about Canarian science if a lot of the institutions here are Spanish institutions? And I just want to give you a little recap. Juanpa, where are you from?
El Hierro.
Where are you from, Alba?
Gran Canaria.
Inés?
Gran Canaria.
Eugenio?
Gran Canaria.
Oh, too many Canariones. Oh my God. here we have one of our beautiful local scholars at GeoTenerife. Obviously, we are adamant that we want to promote local Canarian science. Where are you from, Sergio?
Chile, Tenerife.
Tenerife mainly, right? Javi?
Gran Canaria.
Nice. Can you pass the microphone back to Nieves, please?
I'm sorry, but I'm from Madrid. But I live in Gran Canaria.
I'm from Tenerife.
Sorry? Wait.
I am from Tenerife.
Pablo, I'm sorry. Of course, we have IGN here as well today. Stavros, you are also going to mess this up for me because you are from? Mentiroso. But your boss is Canarian. So with that, we will look forward to some fantastic session after coffee where we're going to hear from some of these young scientists and the incredible research that they're doing here in the Canary Islands. And we encourage you to join us then. Thank you very much, everybody.